record that on the computer. All right, okay. Everyone, so I pressed the recorded button. So in the last lecture, what we did, we learned binary system, zeros and ones, in other words, trues and false, magnetized, unmagnetized, so what these things are, and what we mean by bits. So every time whenever I give a lecture, the first slide I would reserve for recalling what we covered in the previous lecture. So recall that the binary or base 2 number system uses just the 2 digits or bits, which we call them as zeros and ones. To convert from binary to decimal, expand the binary number in powers of 2. For example, if I want to convert 10 into decimal, it would be 1 times 2 to power 1 plus 0 times 2 to power 0. And that would be our expansion in decimal. So in other words, this would be simply 2, right? Well, okay, then what else we did? Let's look at some example. Number 10110.01. This is written in base 2. If I want to write that in real numbers or decimals, what that essentially mean? This essentially mean that this number is 0 times 2 to power 0. This is 1 times 2 to power 1. That is 1 times 2 to power 2. This is 0 times 2 to power 3. And that is 1 times 2 to power 4. Right? Similarly, on the fractional sides, this would be 0 times 2 to power minus 1. And that one is 1 times 2 to power minus 2. So this is written in terms of place values. I mean, how we going to write them. So 2 to power 4 is 16. This number would be 0. That number is 2 to power 2, which is 4. This number is 2 to power 1, which is 2. And then we have this number is 0 when multiplied, you know. And that number is 1/4, and that would be 0.25. And so you sum them up. So this big string of numbers is actually 22.25 in real number system. So now here, keep in mind, also you will calculate them and understand. So in binary, you would have a bigger string, and when you expand them, write them in a bigger basis, like base to base 10, which we usually do in real life. All the numbers are in base 10. So higher the base is, number is slightly smaller. So look at this, 10110.01 to the base 2 is quite big number in terms of string. But when you write that in real numbers, it becomes smaller, as a like 22.25 only. So there are 4 digits in it. Here there are 1, 2, 3, 4, 5, 6, 7. 7-digit number. You wrote that as just 4 digits here when you wrote them in higher bases. Okay. Well, what we essentially mean, if you want to convert an integer from decimal to binary, what we do, we repeatedly divide by 2 and note down all the quotients and remainders at each step until the quotient is 0. All right. Then write the remainders in reverse order. What that means? That if I want to write this number 43 in terms of binary, what I would do, I would write 43 and I divide with 2. When I'm dividing 43 on 2, what I would have 21 would go in 43, and then my remainder is 1. Yeah, 21 times 2 is 42, plus 1 is 43, so 1 is remainder. I divide again with 2, and what I get 10, and my remainder is 1 again. Similarly, I divide again, I get 5, remainder is 0, then I get 2, remainder is 1, then I divide with 1 and remainder is 0. And then what I do, I note down all of this in this order. So I would have, starting from this 1, I would have 1, then 0, then that 1, then 0, 1, 1. So in the reverse order, so I would start from here 1, then I have 0, then 1, then 0, then 1, and then 1 to the base 2. So this is my number 43. All right? Make sense, everyone? So 43 in real, now converted to binary, is this string. So what we don't know at the moment is what happens if I want to convert a number like, for example, this kind of fraction, 1/4, for example, right? If I want to convert that into binary, how I would do that, okay? Now, let me go over some quick facts about that. So the half bits in the binary form of 0.4 is 0. I'll explain that in a minute. So the half bit of 0.4, that means a number which is lower than 0.5 would be 0 and higher than 0.5 would be 1 bit, okay? So if I'm writing that in fraction form, so a fraction less than half would be 0 bits and higher than half is the 1 bit. That's how we regard that. What that essentially means, okay, let me actually, don't worry about this. Let me directly go to the example to make it, just to explain what I mean there. So to convert a decimal fraction to binary, we repeatedly multiply the fractional part by 2 and write down the integers and fraction at each step until the fraction is 0. Sometimes it may not be possible. Sometimes you get repetitions and then you get periodicity. But when we get periodicity, we just stop there. Okay, what I mean by that is, now if I want to convert this fraction to binary, how I would do that? At the moment, okay, so far what I explained is, if you have an integer like 43, what you do, you simply divide it and then note down all those remainders, right? So that was for integer, numbers of this kind. Now, if you have numbers of this kind, which are decimals, fractions, in other words, then how to convert them into binary? The process is you write down the number 6875, all of it, okay, multiplied with 2. All right, so let's multiply with 2. 2 times 5 is 10, all right. 2 times 7 is 14 plus 1, 15, right. 2 times 8 is 16 plus 1 that comes from 15 is 17. 2 times 6 is 12 and 1 from 17 is 13. So 13's 1 that carries forward. That is my my value here that I'm going to list. Right? So at each step, now remember this 6875, these are 4 place values. I would write them and I'll keep multiplying in this way until all those 4 values becomes zeros. So next step is now multiply this 0573 with 2. So 2 times 0 is 0. 2 times 5 is 10, 1 carried forward. 2 times 7 is 14 plus 1, 15, 1 carried forward. 2 times 3 is 6 plus 1, 7. Now for 7, nothing carries forward. So that means my carried forward digit would be 0. Now, the thing that I talked about on the previous slide was half bits. Remember, 3 is less than 5. So that's why the bit that moves or bit that allocated to it is 0. All right? Less than 5 is 0. More than 5 is 1. And the easiest way to calculate them is simply multiply them with 2 and keep noticing all the carried forward numbers. Now, again, since all of these digits are not zeros yet, so I would still keep them multiplying. So 2 times 0 is 0, 2 times 0 is 0, 2 times 5 is 10, right? So 1 carried forward. 2 times 7 is 14, plus 1, 15, and that 1 carried forward would come here, right? And then again, since all of them are not zeros yet, so I would repeat the process. I would have 0, 0, 0, 2 5s are 10, and that 1 carried forward. So hence, this number 0.6875 in terms of binary would be 0. Now for this, I would go from top to bottom, not in the reverse order, but in actual order. I would write them as 1, 0, 1, 1 to the base 2. So this number 1, 0, 1, 1 to the base 2 is my decimal expansion, or is my binary expansion of this fractional number 0.6875. When written in binary would be 0.1011 to the base 2. Any questions, anyone? So there are now, if the number that you're converting to binary is integer, you divide that with 2 and keep noting down all the remainders and list them in the reverse order, right? And if the number is fractional, you multiply it with 2 and keep noting all those carried forward numbers and list them in the order that you get them, and that would be your binary expansion. For instance, if you are to find what would be the binary expansion of 43.6875, so the binary expansion would be binary expansion for 43, which is 101011, point binary expansion for this fraction part, which is 1011 to the base 2. So for integer, successive division. For fraction, successive multiplication by 2s until you get, zeros, right? Okay, so so this method is explained exactly the same way as I did. Questions are done. I really want you to understand them as we go. So few more questions about this, and yeah. So next thing is, this is not the only time. I mean, only how to say, in when we're multiplying successively by 2, there would be scenarios when you can never get 0, right? And if that happens, your decimals would be recurring, or they would repeat themselves. In other words, periodicity would occur. So the method may never end. This is very similar. If you have 2/3, for example, if you divide, if you want to split 2 pizzas amongst 3 people, they would always be, they would never have equal fraction, in other words, right? Yes, that's right, Josh. Your question is, Josh asked a question. Does this mean that for base 3, we would multiply by 3 for a fraction and divide by 3 for an integer? Yes, very similar. And when you have base 3 expansion, allowed digits are 0s, 1s, and 2s only. You will never be having more than 3 digits, right, in their expansions. Yes, that's the precise way that we do that. And I mean, in today's lecture, we'll go beyond binary and we'll do expansions in base 8, all right, as well. We call them octal. Process stays the same, whatever we're doing. Okay, so what I was talking about at this time, that, okay, some fractions never end, all right? and those fractions are called non-terminating fractions. And if the fractions never end, there are two possibilities whether that number is rational or that number is irrational. In all of the questions that we are doing throughout this subject, we will be dealing with rational fractions. We will not be dealing with irrational fractions. So rationals are those where there is a periodicity of digits. Digits after a certain block, they repeat themselves or they stop, right? So if the digits stop, then it's a terminating. If the digits don't stop, but they repeat themselves, then they are non-terminating but periodic. All right, examples. Suppose we have, we want to convert 0.4 into binary. Then the method that we learned was that multiply that with 2. So 4 2s are 8 and carry forward is 0. 8 2s are 16, carry forward is 1. 6 times 2 is 12, carry forward is 1. 2 times 2 is 4, carried forward is 0. Now again, now you see this 4 is the same as that 4 up there. So that means now it would start repeating itself, right? So we can go a bit more and we can write, you can verify that. So after that, as you can see, this block is repeating itself indefinitely. We would never get 0 here, right? So this 0.4 would be 0.0110, 0.0110, and then again 0110, and then again 0110, up to so on. It's your choice that for how many bits you want to repeat it, okay? Normally we go for 8 bits because the 1 byte that we have in computer, that is equals to 8 bits. So we want to fill 8 boxes, right? So normally we'll go to 8 places and then we stop, all right? Now the question is convert 0.65 to binary, all right? If we are asked to do that, well, maybe you want to have a go at this question. If you have a pencil and pen ready, handy, so just try to have a go at it and see what binary expansion you're going to get. I will do the question afterwards, but you first have a go at it, and then once I do it, we'll check who's how our attempt was. Yeah. So I'll give you a couple of minutes to do this question. Okay. Well, with 0.65, if I want to convert that to binary, so I put 65 there and started multiplying with 2. When I first time multiplied with 2, I got 130. So, but I am only allowed 2 places here. So 3, 0, and 1 would be carried forward. And then 30 times 2 is 60. So that 0 would go carried forward. 60 times 2 is 120. So on the third place, we'll get 1. And then 20 times 2 is 40, carry forward 0. 40 times 2 is 80, carry forward 0, up to so on. And then we simply list these numbers to get our binary expansion of these fractional parts. Yeah. Okay. So this answer would help us to calculate. So this is my answer. If your answer is slightly different to it, so we may want to verify that again or check it again, who's correct and who is incorrect, right? Remember, there are lots of tools on internet where there are online calculators. If you put a number, it will give you binary expansion straight away, all right? So what we are doing, we are understanding underlying mechanism, that how it's being done, right? And how computers work, basically. All right, so next exercise is by looking separately at the integer and fractional parts, convert this number to binary. So 0.65, we have already converted that to binary in the above exercise. So we only have to convert this integer part into binary. Okay, so anyone having an answer yet?
I've got one.
Yes, Jack, what is it?
I had 10011.101.101001.
Okay, 10011.101001 to the
I had an
base.
extra 0 in the start of it.
Okay, there's a 0 missing. Where?
I'll just put my book up to it. It might be back to front though because of the camera. I'm not sure.
Oh, yeah. So there's 1 0 missing here. That's what you're saying.
Yeah.
Great. Okay. Let's verify that quickly. 0.65 we have already done, so I am only doing 35. So on 2, it would be 17.1814020 and then 10. Yep. So it's 1000011. That would be my yeah, this number. That's correct. Fantastic. Anyone? Any questions as such yet? Okay. So if this method is clear, we should be able to move now to other bases. So what we did, we have decimals. By decimal, I mean real numbers that you're aware now. Well, decimals, and we learn how to convert decimal into binary, binary into decimal. Now, what we want to do, we want to introduce another system. We call that octal. Yeah, octal system. And that means the base is 8 now, right? Remember, in our bits here in computer, you always deal with, oh, my RAM is 128 megabits. Why 128? Why not say 100? Why not say 200? Or, yeah, the hard drive is, let's say, 256 gigabits. Why it's like, you know, always in powers of 2s? There is a reason for that. And those reasons we want to understand why it is so, okay? In terms of mathematics and all that, because everything is based and built on this binary, right? So when we are moving from base 2, it's easy to convert between any other bases if they are powers of 2. All right. So we'll try to understand all the underlying reasons that why we do so. Okay. Well, let's look at the octal number system. The method for converting from binary to decimal and vice versa extends to bases other than 2, as I just said. So base 8 system, remember, 4 and 4. Ignoring thumb counting, you will be on just, if you're only finger counting, that's exactly actually 8, right? We'll look at conversions between octal and decimal, and then at why octal is useful in computing. Remember, every time need to improve is based on some kind of efficiency issues. So conversions between binary and octal are extremely easy, but in terms of space and there are some drawbacks as well. That's why there would be need to improve on and introduce higher bases, right? So what is octal? Octal uses the digits 0, 1, 2, 3, 4, 5, 6, 6. That's it, right? 7 will become 0 again, right? So you are not allowed to go further than that. So they're just like in 10 digits, you have 0 to 9 distinct digits that you use. Similarly, with 8, you would have 0 to 7 distinct digits. The place values are powers of 8 now. So for example, if I want to convert this number to decimal, right? So this is written in base 8 system. So this means this number is 3 times 8 to power 0 plus 5 times 8 to power 1 plus 2 times 8 to power 2, 6 times 8 to power minus 1, 4 times 8 to power minus 2. The place value system, exactly. So if I want to convert this number into decimal, okay, naturally, just imagine whether the number you would get would be smaller than 253.64 or bigger than 253.64. If you expand that in base 10. I can't hear you if you're saying anything because it's muted. All of you are muted.
Bigger?
Bigger. Okay. Anyone else? Only 2 choices.
Smaller.
Smaller. Yeah, so bigger or smaller, one of them should be true, right? Yeah, okay. Well, as I described at the start of a lecture, if I'm expanding a number from a lower base to higher base, the resulting number would look slightly smaller. And if I'm expanding from a bigger base to a smaller base, then the string would increase. Just like in binary, you have a longer string, and when you express that in decimal, you get very small number, right? In other words, so 8 is still smaller than 10. So when I'm expanding a number which is written in base 8, and if I'm writing that in base 10, the resulting string would be slightly smaller than the string that I have now. Okay, let's look at that. Let's verify it. Okay, so 2 times 8 square is 2 times 64. 5 times 8 is 40, 3 times 8 power 0 is 1, plus 6 over 8 plus 4 over 64. This is equals to 2 times 64 is 128, 5 times 8 is 40, plus 3 3/4 is 0.75, right? And plus 4 over 64, which is 1 over 16, that would be 0.0625. I've simply actually, you don't have to calculate that. You can leave that as it is. So this number is going to be 128 plus 40 is 168 plus 3, 171, right? Then you want to add 0.75 with 0.0625. 5 2 6 5s are 11, so you would have 8. Yeah, 0 sorry, what happened this here? That would be 8125. So in other words, this octal number 253, right, 0.64 in decimal expansion become 171.8125. Now you can see, if I have expanded a number in base 10 in our usual base, right, a number which was written in base 8, when I rewrote it in base 10, 253 converted into 171. So resulting number is slightly smaller because I'm expanding in higher bases. Okay. So the same way as we expand real numbers, we're gonna do the powers of 8 as well. I have written this solution is proper form there. So yeah, that's how we do that. Okay. And similarly, this is the conversion from octal to decimal. Same way as we did from decimal to binary, we'll do decimal to octal. All right. So, but before that, just an exercise. So convert 172.4. It's written in octal. If we can convert that into decimal at this stage. So that would be 1 times 8 squared plus 7 times 8 to power 1 plus 2 times 8 to power 0 plus 4 times 8 to power minus 1. 64 plus 56 plus 2 plus 4 over 8 is 0.5. So that should be equals to 122.5. I think that's the only reason I can do slightly quickly, because I've done them already before several times. So it's just practice. More practice you do, more fluent you would be on these kind of conversions and all that.
I just have a question. What would the graph look like if you were to say base 1, base 2, base 3, base 4 of the same number? Would it be a straight line? Or would it be like a curvy line? Does that make sense? As in, so base 8 of 172 is 122 in base 10. So
yeah,
base 9
up to certain
would be
constant. Up to certain constant, there is a direct relationship with them.
So it'd be a sort of a straight line.
I would have to think. Okay. You can convert them up to a logarithmic factor. That logarithmic factor would stretch the line a bit. Okay, so. But then you want to make one of the variable continuous, right, with the other. So in base 10 expansion, you're expanding a number, and then you are converting them in base 2. So you would have like a, sort of a straight line. Yes, up to a certain fraction. Anyway, we'll deal with that later.
Sorry, that's a tangent. Yep.
Maybe. Yeah, tangent would be a logarithmic of the base, basically. Yeah. Anyway, converting from decimal to octal. So remember, every time, whatever basis we are taking, we will always be trying to convert between binary, decimal, and the base we are considering. Okay, how the conversions work. Now the question is converting from decimal to octal. So you recall how you converted from decimal to binary. What you did, if it's an integer, you divided with 2 successively and noted all the remainders, right? And then with the fractions, you multiply them with 2, right? And noted down all the carried forward, or the places values, carried forward numbers. Now here, exactly the same process. Instead of 2, you would have 8. Okay. So for example, if I want to convert this number to octal, all right. So what I would do, I would have, firstly, I would deal with this integer separate, and then the fraction part separate. So writing down integer 103, I would like to divide with 8. Okay. If I'm dividing this number with 8, we would have, how many times 8 will go? 103. So it will go 12 times. 12 8s are 96, and your remainder is 7, right? And then how many times 8 goes in 12 is 1, and your remainder is 4. Hence, your 103.6 converts to 147 point. So again, exactly the same process. This number 147, that is the conversion from integer to that. Okay, integer to octal, right? The next step is to convert the fraction part, which is 6, into octal. So you multiply with 8 and see what we get. 8 times 6 is 48. So 4 is this value there. 8 times 8 is 64. So 6 goes there. 8 fours are 4 times 8 is 32. So 3 goes there. 8 times 2 is 16. 1 goes there. And then there is a repetition. 8 times 6 is 48 again. So after that, it repeats itself. So my digits are 4, 6, 3, 1, and then 4, 6, 3, 1, up to so on to the base 8. So exactly the same process as you would have decimal to binary. Now you have octal to, binary to decimal, or decimal to binary. Now you have decimal to octal, and similarly we would have octal to binary if we would do that soon, actually. So remember, so what are the what we have decimal to binary, but we noticed that binary strings become larger and larger, right? So we should have slightly better way of representing them. So as a better way of representation, we came up with octal. Okay, octals are a good shorthand for binary because I can write every number as 2 to the power 3 as 8. All right. Now, what we learned so far, how to convert between decimal and octal. What we have not done yet is the conversion between binary and octal. Yeah. Which we will actually do soon. But before that conversion, let's look at this in one more exercise. Let's do to convert a decimal into octal numbers, right? So recall, if I want to convert integer into an octal, what I would do, I would just divide by 8. And for the fractional part, I would simply multiply by 8 and note down all those carried forward. So hence my result, which I just calculated on the previous slide, is this number. Based on this method, can I ask you to have a go at this number and see what your octal representation would be for that? So my answer to this question is 73.44. How did I do that? I divided 59 on 8. 8 sevens are 56. So 7 is here and remainder is 3. I cannot further divide it, right? Because these digits are already smaller than 8. So my for the digit part, my answer is 73 point. Now 5625 you multiply with 8. When I first time multiply, I got 0, 0, 0, 5, and on the 5th place I would have 4, or carried forward would be 4, so that 4 goes there. And then again I multiply with 8 to get 0, 0, 0, and 8 fours are 40. So 4 would be carried forward again. So my decimal expansion is 0.44. Any questions, anyone? Right, okay, so that is the that's my answer, and I hope you got very similar answer as well for that. So why we are studying octal, and why there's a need to go beyond octal, why there was a need to go beyond octal. So what are the advantages of octal and what are the disadvantages? All right. Few advantages I have already explained, that okay, these are actually so internally, as we all know, computers use binary numbers exclusively, right? In each box we have either on or off. Each bits is like 0, 1, right? And they're only in binary, okay? However, binary numbers often have many digits. For example, 9,000, if I'm writing 9,000 in binary, that would be this long string of numbers. Yeah, so string is quite long. So binary numbers aren't good to use for use by humans because the strings are quite long, right? It's easy, but if I'm converting 9,000 into binaries, then it will be quite a long string of numbers. Or if you have 1 billion in decimal and you want to convert that into binary, that would be quite a long number, right? So that the longer the string goes, there is a high tendency that you might skip or miss a 0 or 1 here and there. So that may leads up to transcription errors or decoding errors and all that. Okay. Decimals, of course, uses fewer digits than binary, so might be considered to be a good shorthand for binary. But conversion between these bases is awkward. So if I want to convert between base B and C, there is a difference of logarithmic order difference, which is log is a nonlinear quantity. So anyway, so the conversions are not that easy. If I want to convert, let's say to the base 10, a number which was in base 3 and something like that, then the conversions become quite challenging. Or conversion from 2 to 10, we already seen that the strings are quite long. However, conversion between 2 and 8 is quite simple because 2 to the power 3 is 8. Or conversion between 2 and 4 is quite simple because 2 square is 4. Similarly, conversion between 16 and 2 is also simple because 2 to the power 4 is 16. So the conversions between in the powers of 2 and binary, it's very easy. Yeah. So it has two advantages. Octal has now two advantages. One, it has fairly large base, right? So integers and terminating fractions won't have too many digits in them. And second, it's easy to convert between octal and binary. Very easy to convert, actually. That we would do in the next lecture. However, then I would also explain that there is a disadvantage as well in using octal. All right. So we'll do that in the next lecture, which either we can start right now and continue until that finishes, or we take a break if you like. Anyone in favor of break? 5 minutes, 5 minutes, 5 minutes. All right, so let's take 10 minutes break and we jump in again in 10 minutes and we resume our lectures, yeah? All right, so see you soon in 10 minutes, everyone.